So on this one, we're working on an exponential equation that we want to solve. 2.65 to the x equals square root 7 to the 1 minus 2x. So this is an equation, an exponential equation. I have three methods that I typically use to solve exponential equations. That's to make the bases the same, to convert to a log, or to take the log of both sides. So at first glance, you might think that you are able to make the bases the same, because if you were to type square root of 7 in your calculator, it is approximately 2.65. So they're not exactly equal, but they are pretty close to each other. So if we were only looking for an approximation to this answer, then we could use making the bases the same, relating the bases to solve this. But we need to be exact. So to be exact, we're going to use the other two methods, which is to convert to a log or to take the log of both sides. Now both methods work just fine, but I typically prefer to use taking the log of both sides because I use natural log. And natural log is usually on the home screen of your calculator. So it can, once you get to the answer is easier to type in the calculator because it's using natural logs. So I'm going to take the log of both sides. So I'll do natural log on the left, natural log of 2.65 to the x, and natural log on the right, natural log of square root of 7 to the 1 minus 2x. And then we can use the power rule for logarithms, and the power rule for logarithms allows us to move this variable out of the exponent. So it's moved into the coefficient of the log, or multiplied by the log. So that would give x natural log of 2.65 equals 1 minus 2x natural log square root of 7. And then on the right-hand side, we're going to use the distributive property and distribute this natural log square root of 7 to both terms. I'm leaving the left-hand side alone. Distributive property on the right-hand side, that gives natural log square root of 7 minus 2x natural log square root of 7. So now I want to start grouping like terms together. So I'm going to group the x terms onto one side of the equation and the terms without x on the other side. So these two have an x in them. I want them on the same side, so I'll move it to the left. And this term doesn't have a variable in it, so I'll leave it on the right-hand side. That's going to give x natural log of 2.65 plus 2x natural log square root of 7 equals natural log square root of 7. So now I've got that organized in a way so the variables are on one side. I can factor that variable out. So I'm going to factor an x out of both of those terms, leaving with natural log of 2.65 plus 2 natural log square root of 7. And the right-hand side stays the same. And finally, I can get x by itself by dividing by what's in the parentheses, dividing by natural log of 2.65 plus 2 natural log square root of 7. And so we've got a solution. I'll write it over here. X equals natural log square root of 7 over natural log of 2.65 plus 2 natural log square root of 7. So this would be our exact solution to the equation. Let's pull up our calculator and get the approximate solution. So we'll type natural log square roots, let me try that again. Natural log square root of 7 for the numerator And I didn't need a parenthesis around the numerator because there's only one term in the numerator, but I do need parentheses in the denominator. It's natural log of 2.65 plus 2 natural log of square root 7. And I'm going to close parenthesis for the log and close parenthesis for the denominator. And we get 0.3331. Let's round that up to 0.3332. Okay, so if you'll recall, I'm just going to do one more thing on this problem. If you'll recall, I mentioned that if we just need an approximation, we could make the bases the same. So I just want to quickly show you that approach. 2.65 to the x equals square root of 7 to the 1 minus 2x. So if we're assuming that these bases are the same, we can say that the exponents are equal to each other. X equals 1 minus 2x. We would add 2x to both sides and get 3x equals 1. Divide by 3 and we get x equals 1/3. 1/3 is 0.3333 repeating, right? And so we got really, really close to the right answer with this approximation way of solving it. But in your homework, you're asked to round to, I think, 4 decimal places. So if you do it the approximation way, you're going to get it wrong because it's wrong on that 4th decimal place. How long will it take for an investment to triple if it's compounded continuously at 6%? So first thing I notice here is compounded continuously, and those key words are telling me which formula to use to solve this problem. It's going to be our continuous compound formula of A equals PE to the RT. So then I'm going to start looking for information to help me substitute into this formula. And really the only number that's given is this 6%. So this is going to be R, the interest rate. So we have a 6% interest rate. And in the formula, we want to use it in its decimal form, 0.06. If I take a closer look at the problem, the question is phrased, how long? So I'm trying to solve for time in this question. And the only other information is that we are trying to triple our investment. So this doesn't give us any specific numbers, but it does tell us the relationship between the amount we start with and the amount we end with. So this is going to tell us that we want to end up with 3 times the amount that we start with. So we can now substitute this information into our formula and be able to solve for time. So starting with our formula, A equals PE to the RT. A is 3 times P. It's trying to triple the amount we started with. We have an interest rate of 0.06 times time. So our goal is to solve for time, which is in the exponent. Now, our techniques for solving exponential equations require the exponential expression to be isolated. So I need this portion right here to be isolated on one side of the equation. So I'm going to divide both sides by P to isolate that exponential. And this is a great step here because the P's, which we didn't know anyway, cancel from both sides of the equation, giving us 3 equals e to the 0.06t. And now we can use one of our techniques for solving the exponential equations. Remember, we can make the bases the same. We can take the log of both sides. We can convert to an exponential. So I practiced taking the log of both sides today, so I'll practice converting. So if I were to convert, I would write the word log, and the base is going to be the base of the exponential, so I have a base of e. The log always equals the exponent. My exponent is 0.06t, and then this 3 is what gets substituted inside the log. I'm going to rewrite it without the colors, and also we don't typically write log base e. We have a special notation, which is natural log of 3. Natural log of 3 equals 0.06t. And then I can divide both sides by 0.06 to solve for a time. So we have natural log of 3 over 0.06. I'll type this in my calculator. So we're doing natural log of 3 over 0.06. And we have 18.31. We want to round to the nearest year, or we would round up to 19 years. We're going to round up because rounding down wouldn't guarantee us to meet that tripling amount. So we're going to round up to 19. So that's not our normal rounding rules. Our normal rounding rules are if it's 5 or more, you round up. Less than 5, you round down. But we want to guarantee that our investment triples, so we need to go over whatever our answer is to guarantee that we triple the investment by that amount of time. The population of Adamsville grew from 7,000 to 11,000 in 7 years. Assuming uninhibited exponential growth, what is the expected population in an additional 4 years? So we have stated in the problem, assuming uninhibited exponential growth. So there are two formulas that are really the same formula using just different letters. So you can use the formula with p's for population. P of t equals p naught e to the kt. The one with a of t equals a naught e to the kt. Like I said, they're really the same formula. P for population, a for amount. And this is the model assuming uninhibited exponential growth. So let's look through the problem to see if we can identify any variables. We've got the population growing from 7,000 to 11,000. This would be a starting population and an ending population. So that would be like your P naught. P naught would be your starting population, and then P of t would be your ending population. 7 years, that would be a time. And then it's asking what is the expected population in an additional 4 years. So we're given another time. So in this question, the information that's given in the first part is meant to help us find K, which is the growth rate. So we need to start off by finding that growth rate, and then once we've found the growth rate, then we'll be able to answer this question that's posed at the end. So let's start off finding that growth rate K. So the 7,000 would be an initial population. The 11,000 would be the population after 7 years. So that's P of 7 would be 11,000. And we have our t being 7 for 7 years. So looking at our formula, we have something to plug into this spot. That's the 11,000. Something to plug in this spot, that's the 7,000. And something to plug in this spot, which is the 7 years. And that means we're going to be able to solve for that growth rate. So we have our formula, P of t equals P naught e to the kt. Substituting in, we get 11,000 equals 7,000 e to the k times 7. To start solving this, I want to isolate the exponential, so I'll divide by 7,000 on both sides. You can cancel out some of those zeros and get 11 over 7 on the left. And on the right, I'll have e to the 7k. I've got my exponential isolated, and I can solve this by taking the log of both sides. Do natural log on the left and natural log on the right. On the right-hand side, the natural log and e are inverses of each other. They cancel each other out. You get 7k. I can divide both sides by 7 to get my growth rate. The growth rate is natural log of 11 over 7 over 7. So now I know the growth rate, and I can answer this question: what is the expected population in an additional 4 years? So there are a couple different ways to go about this next part. It depends on what you consider your starting population, your ending population, your beginning time, and your ending time. So you can set this up different ways. I'm going to start it from our beginning, which is starting with a population of 7,000. So I'm going to use P naught equal to 7,000. And our k, we already figured out, natural log of 11 over 7 over 7. Our time, because I'm starting from the beginning, I need to consider the 7 years and the additional 4 years. So that will be 7 plus 4, which is 11. So this is what I'm going to substitute into my formula. Remember, it's P of t equals P naught e to the kt. So P of 11 years is 7,000 e to the natural log of 11 over 7 times 11. In my calculator, I'm going to type 7,000 e to the 11 natural log of 11 over 7 like this, so I don't have to use as many parentheses. That's 7,000 e to the 11 natural log 11 over 7 over 7. So we get that that population has now grown to 14,240, let's round to 2. 14,242. I'm going to zoom out so you can see the whole problem. And maybe I'll show you the other way. So what if I had started with the 11,000 as my starting population? And then k is still going to be natural log of 11 over 7 over 7. But here, since I already started after the 7 years, I only need to do the additional years. So I would make this P of 4, 11,000 e to the natural log of 11 over 7 times 4. So let's type that in and see if we get the same answer. Hopefully we do. 11,000 I'll do the 4 first. Oops, I need the e. E to the 4 natural log of 11 over 7 over 7. And we get the same answer, 14,242. A certain radioactive isotope has leaked into a small stream. 200 days after the leak, 15% of the original amount of substance remained. Determine the half-life of this radioactive isotope. So our goal is to figure out the half-life. The half-life is the time to decay to half of the original amount. So I'm going to start with the original information of it taking 200 days to get to 15% of the original amount. This information is going to help me find K, the decay rate. And once I find the decay rate, then I'll be able to find the half-life. So I'm going to use this formula here, A of t equals A naught e to the kt. And we know that it takes 200 days for us to get to 15% of the original amount. So it didn't give me any specific numbers of how much you started with or how much you ended with, but it is giving me that after 200 days, 15% of what you started with remains. So I'm able to build that relationship. A is equal to 0.15 A naught. I'm going to substitute this information into the formula and solve for K, the decay rate. We call it a decay rate because we are losing the amount instead of growing to a larger amount. So in our formula, A of t equals A naught e to the kt. We have A naught and 15% of A naught and e to the k times 200. I'm going to isolate the exponential by dividing by A naught on both sides. That's 0.15 equals e to the 200k. Then I'll take the natural log of both sides. It's one of my techniques for solving exponential equations. And natural log and e are inverses, so they cancel each other out. So I've got 200k on the right and natural log of 0.15 on the left. I'm going to divide by 200 and get k is equal to natural log of 0.15 over 200. This is our decay rate. So I can use that decay rate to find the half-life. So the half-life is the time, that's what we don't know, the time it takes for us to get half of the original amount. So I'm going to use the k that we just found, natural log of 0.15 over 200, as well as this relationship that we're looking for half-life to solve for time. We have A of t equals A naught e to the kt, that's our formula. Because we're looking for half-life, our amount will be half of the original amount. And our k, we're going to use the natural log of 0.15 over 200. So we're going to solve this exponential equation by dividing by a naught on both sides. That cancels out a naught on both sides, leaving us with 1/2 equals e to the natural log of 0.15 over 200 times time. We'll do the natural log on the left, the natural log on the right. Because we've introduced the natural log, we can now use the power rule, or actually we can use the inverse properties. Natural log and e cancel each other out. We have natural log of 1/2 on the left, natural log of 0.15 over 200. I think I've written that wrong. I think the 0.15 is inside the log and the 200 is not. Let me zoom out to make sure I've got it right. Yeah, that's correct. Okay. So I'm going to get t by itself. I'll divide both sides by natural log of 0.15 over 200. So we've got t equal natural log of 1/2 divided by natural log of 0.15 over 200. When we're dividing fractions, we multiply by the reciprocal. So that's natural log of 1/2 times 200 over natural log of 0.15. So we can write this as 200 natural log of 1/2 over natural log of 0.15. Let me zoom out. We'll type that in our calculator. So we're going to put parentheses around the numerator, 200 natural log of 0.5 divided by natural log of 0.15. So it would take 73 days to decay to half of what you started with. So we have a half-life of approximately 73 days. On this one, we want to use the properties of logarithms to expand the logarithmic expression, and whenever possible, evaluate logarithmic expressions. So that means that when you have log of a number, try to simplify it. If you have log of a variable, you probably won't be able to simplify it. So one thing that I want to recognize about this is I've got a radical in this problem. And having a radical is the same thing as having an exponent as well. So instead of writing square root of x, we're going to write that as x to the 1/2 power. And we're going to expand using some log properties. We're going to expand using the product and quotient rule. And using the product and quotient rule means that you're going to look for factors inside your log, both factors in the numerator and factors in the denominator. So we've got one factor in the numerator of square root of x. In the denominator, we have 1,000 and y to the 5th. So with the product rule and the quotient rule, we're going to be able to expand this into 3 different logarithms for those 3 different factors. So we're going to have log of x to the 1/2 power, log of 1,000, and log of y to the 5th. Now, with the product and the quotient rule, the way it works is you're expanding into addition and subtraction. So in between these logs, I should have either pluses or minuses. And if we had a factor coming from the numerator, that log should be positive. A factor coming from the denominator, that log should be negative. So both of these will have minuses in front of them because 1,000 was in the denominator and y to the 5th was in the denominator. We're going to continue to simplify this using another log property called the power rule. And when you have a power inside the log, like both of these do, you can move that exponent into the coefficient. So we're going to move it in front of these two logs. So this becomes 1/2 log x, and this one becomes 5 log y. And then this one in the middle, because it's log of a number, we want to try to simplify it. So with this one, it's a little bit tricky because no base has been written here. So we have to know that this is base 10. So when we simplify or evaluate this log, we need to say 10 to what power is 1,000, and 10 to the 3rd power is 1,000. So that means log of 1,000 is 3. So we've got our fully expanded expression here as 1/2 log x minus 3 minus 5 log of y. On this one, we want to solve the exponential equation. 14 to the 3x minus 1 equals 5 to the x plus 1. So to solve this exponential equation, we can take the log of both sides or convert to an exponential. I prefer to take the log of both sides because it'll be easier to type in my calculator later. So I'm going to do the natural log on the left and the natural log on the right. And I can use the power rule for logarithms to move this exponent into the coefficient. This would give me 3x minus 1 natural log of 14 equals x plus 1 natural log of 5. And then I'm going to use the distributive property to distribute this log to both terms. And I'll do the same thing on the right-hand side of the equation, the distributive property. So that's going to give me 3x natural log of 14 minus natural log of 14 equals x natural log of 5 plus natural log of 5. Well, now that I've got it all expanded out, I want to start grouping the terms together. I want to group the x terms to one side of the equation and the terms without x to the other side. So I've got these two terms with x, and I'm going to group them onto the left-hand side of the equation. These two terms without x, and I'll group them on the right-hand side of the equation. So that's going to give 3x natural log of 14 minus x natural log of 5 equals natural log of 5 plus natural log of 14. Once you've got those x's grouped on one side, you can factor the common x out. That would give 3 natural log of 14 minus natural log of 5 equals natural log of 5 plus natural log of 14. We've got one more step here, and that is to isolate x. So we'll divide both sides by what's in that parenthesis, natural log of 14 minus natural log of 5. So our final answer will be x equals natural log of 5 plus natural log of 14 divided by 3 natural log of 14 minus natural log of 5. Let's try typing this in the calculator. And just like other problems that we've done here, if we have multiple terms in the numerator or denominator, we need to put parentheses around them. So we'll do parentheses around the numerator, natural log of 5. I need to close parentheses. That's something I forget a lot. I'm going to close parenthesis on that natural log, plus natural log of 14, and close parenthesis for that log, and also close parenthesis for the whole numerator. And then I'll divide, and I need parenthesis for the denominator. That's 3 natural log of 14, closing parenthesis for that log, minus natural log of 5, closing parenthesis for the log and for the whole denominator. And that will give us 0.6735 for our approximation for that log equation. We want to solve this exponential equation. 5 times 11 minus 10 to the 3x minus 4 equals 8. So all of our techniques for solving exponential equations involve the exponential portion being isolated on one side first. So on this problem, we have to do a bunch of work before we can use our techniques. So we're going to start by dividing both sides by 5. And that gives 11 minus 10 to the 3x minus 4 equals 8/5. Subtract 11 on both sides. That gives negative 10 to the 3x minus 4 equals 8/5 minus 11. I need a common denominator, so I'll make that 11 over 1 multiply by 5 over 5, so I can get that common denominator. 8 over 5 minus 55 over 5, which is that negative 47 over 5. Somehow that doesn't feel right, but we'll go with it. Okay, so negative 10 to the 3x minus 4 on the left. And we're almost isolated, so we're going to divide both sides by negative 1. And that gives us our isolated equation, 10 to the 3x minus 4 equals 47 over 5, positive 47 over 5. So now that we have that exponential isolated, we will use one of our techniques. We can take the log of both sides. We can convert to an exponential. And on this one, because I have a base of 10, I'm going to convert to an exponential because a base of 10 is something that I do have on my home screen. So I'm going to convert this to a log. We're going to use a base of 10. The log always equals the exponent, so it's going to equal this 3x minus 4 that's in the exponent. And then the 47 over 5 is what goes inside of our log. So when we have base 10, we don't have to write that base. So we have log of 47 over 5 equals 3x minus 4. And I'm going to solve for x by adding 4 to both sides. 3x equals log of 47 over 5 plus 4. Divide by 3. And we have our solution of x equals log of 47 over 5 plus 4 over 3. And let's type that in our calculator. I'm going to use log, that's log base 10, and I'm going to clear this because I need parentheses around my whole numerator. Log of 47 over 5, close parenthesis for the log, and plus 4, close parenthesis for the numerator, and I'll divide by 3. I don't need parentheses around the denominator because there's only one thing in the denominator. So we get 1.65 for our approximation. And that should be rounded 1.66. Let me zoom out so you can see the whole thing. On this one, we want to solve the logarithmic equation, log base 5 of x plus 2 plus log base 5 of x minus 2 equals 1. So when we are solving logarithmic equations, there are two basic techniques that we typically use. And the two techniques are to convert to an exponential, and to also, the other one is to, it's called the property of equality. So it looks like this. So if you start off with something like this, y equals log base b of x, this is when you would convert to a log. When you have log only on one side, and that would give you b to the y equals x. The other technique is for when you have log base b of something on the left and log base b of something on the right. So you'll notice that you have logs with the same base on both sides, and this is the property of equality, and you say what's inside the logs are equal to each other. So this is the other technique. So when I'm looking at this equation, I notice that the logs are both on the left-hand side. So with the log only on one side, I'm going to use the method of converting. But in order to use that method of converting, you need to have a single log, just one log. So before I can convert, I need to use my log properties to condense. They do have the same base, so I'm allowed to condense. And this is adding, so I'm going to condense with the product rule, and that means that I multiply what's inside the logs together. So that's going to give me log base 5 of x plus 2 times x minus 2. So I'm using the product because I have the sum of logs with the same base, and that's how I decided to multiply inside. So now that I have a single log on the left, I'm going to convert to an exponential. My exponential will have a base of 5. The log always equals the exponent, so it'll have an exponent of 1. And this exponential will equal what's inside the log. So it will equal x plus 2 times x minus 2. So I'm going to multiply the right-hand side out. The left side, 5 to the first power is 5. If we multiply this out, we would get x squared minus 2x plus 2x minus 4. Combine like terms, and I have x squared minus 4 on the right-hand side because that negative 2x and plus 2x cancel each other out. I'm going to add 4, and that gives x squared equals 9. Square root both sides. And we get x equals plus and minus 3. Now we've got what x equals, but with log equations we're not done here, because when we solve log equations, sometimes we can produce what we call extraneous solutions. And extraneous solutions are solutions that don't work in the original equation. So every single time you solve a log equation, you have to check for those extraneous solutions. So we're going to check x equals 3 and x equals negative 3 in the original equation. And what we're looking for is whether these numbers are in the domain of those logs. We can only take the log of positive values. So we have to exclude any time we take the log of a negative. So let's check x equals 3. In the original, that would be log base 5 of 3 plus 2 plus log base 5 of 3 minus 2 equals 1. So what I'm checking for, 3 plus 2 is 5, which is a positive. 3 minus 2 is 1, which is a positive. So 3 is in the domain of both of these log expressions. I'll be able to keep that. Then we'll check the other one. x equals negative 3. Log base 5 of negative 3 plus 2 plus log base 5 of negative 3 minus 2 equals 1. Negative 3 plus 2 is a negative 1. And log of a negative is undefined. Negative 3 minus 2 is negative 5, and log of a negative is undefined. So negative 3 cannot be a solution to this equation because it produces these undefined portions. So we have to throw that solution away. The only solution to this equation is x equals 3. On this question, we want to determine the real solutions to the system of nonlinear equations. We have x squared plus y squared equals 4. X squared plus y minus 2 squared equals 1. So these are both circles. So when we have circles, we can have, let's see how many, we have 2 circles, we could draw them like this and have 2 intersection points, which means 2 solutions. Trying to think if there's a way I can draw 2 circles and get 4 solutions. I don't think so. I know we can get 1 solution. And we can get no solution. So when solving this, we could use substitution or elimination. I will solve this with elimination, and I'm noticing that I have x squared in both of these equations. So in order to use the elimination method, I'll need to multiply one of the equations by negative 1. So I'll multiply negative 1 times the second equation, and I would get x squared plus y squared equals 4. Negative x squared minus y minus 1 squared equals negative 1. I can add these equations together. The x squareds will eliminate, and I'll have y squared minus y minus 1 squared equals 3. In order to solve what I have left, I need to clean up the parentheses and combine like terms. So y minus 1 squared, that's y minus 1 times y minus 1. And y minus 1 times y minus 1 will simplify. I'm going to put a bracket here because of this minus. I need to make sure that this minus applies to everything behind it. So I'm going to put that bracket there to make sure that I don't mess up with the negative later. So when I multiply this out, I would have y squared minus y plus 1 equals 3. That's y squared minus y squared minus 2y plus 1. So I combined like terms inside those brackets. I'll continue up here. And now I'll distribute that negative. Y squared minus y squared plus 2y minus 1 equals 3. Y squared minus y squared will cancel each other out. We have 2y minus 1 equals 3. I'm going to add 1 to both sides to get 2y equals 4. Divide by 2 and y equals 2. So I have the y coordinate and I'm going to find the x coordinate. So I'll substitute that 2. I'll use the first equation. X squared plus y squared equals 4. That's x squared plus 2 squared equals 4. X squared plus 4 equals 4. Subtract 4 on both sides and I have x squared equals 0. And x equals 0. So the solution that we get for this system is the ordered pair 0, 2. On this example, we want to solve the system. It specifically says to solve it by substitution, so we'll make sure to use that method instead of elimination. And when we look at this system, we have negative 2/3 x plus 1/3 y equals negative 1/9. and negative 3/4 x plus 2/3 y equals negative 2/9. So to start off, it has a bunch of fractions, which can be challenging. So what I'm going to do is take a step before we start any of our normal strategies for solving systems. I'm going to take a step that's called clearing fractions. It'll get rid of all the fractions in the problem so that we don't even have to deal with them, at least at the beginning of the problem. So with this clearing fractions method, you need to look at all the denominators. So for this first equation, we have 3, 3, and 9. And if we were going to find a common denominator between 3, 3, and 9, it would be 9. So in order to clear the fractions for this equation, I'm going to multiply by 9 on both sides. I multiply by a 9 on the left and a 9 on the right. So on the right-hand side, those 9s cancel. So the new equation is going to equal negative 1. On the left-hand side, I'll distribute that 9 to both terms, so we'd have 9 and 9 when we distribute. 3 goes into 9 3 times, and we'd have a negative 6x there. And 3 goes into 9 3 times, and we'd have a plus 3y. So we were able to clear the fractions from that first equation. We're going to do the same thing for the second equation. So I need to look at those denominators. I have 4, 3, and 9. So if I were finding a common denominator between 4, 3, and 9, that would be 36. I'm going to multiply by 36 on the left-hand side and 36 on the right-hand side. I got 36 by multiplying 9 times 4. So I distribute that 36 to both terms on the left, so 36 and 36. 4 goes into 36 9 times. 9 times 3 is 27, so I have a negative 27x. And 33 goes into 36 12 times. 12 times 2 would be 24, so I have a plus 24y. On the right-hand side, 9 goes into 36 4 times. 4 times 2 is 8. I have a negative 8 on the right. Let's write that in black. So that's a little bit better, because I no longer have any fractions in the problem. But now I have to solve with substitution. So you can solve for any variable you want. I'm going to solve for this y. I have negative 6x plus 3y equals negative 1. I'll add 6x to both sides. And that's 3y equals 6x minus 1. Divide by 3. And I have y equals 2x minus 1/3. Then you're going to substitute that into the other equation. We were able to avoid fractions for a little while with clearing fractions, but because we had to use the substitution method, we couldn't avoid it totally. So I'm solving for y and substituting in for y. And when I substitute in, I would get negative 27x plus 24 times 2x minus 1/3 equals negative 8. And I'm going to distribute that 24 to get negative 27x. 24 times 2 would be 48x. And 3 into 24, that's going to go 8. I can combine like terms here. 48 minus 27 would give me 21x minus 8 equals negative 8. Add 8 to both sides and get 21x equals 0. Divide by 21 and get x equals 0. Then I'll take this 0 and substitute it in for x to get y. Y is equal to 2 times 0 minus 1/3. And that is 1/3. So we get a solution of 0, 1/3 for this system. Let me zoom out so we can see the whole thing. We cleared fractions and then used the substitution method to solve. Thank you for checking out my videos. Have a great day.